So this is ray optics and this is still unfinished. That is, I still have more to write in this note, but yeah, I have a headache and that's why I'm just ending it here for now. And I will continue this for some time. Once I'm done with it, I will start uploading the questions of optics, right? So I will solve the modules and everything, but that's once I'm done with this. So yeah, what is this? Well, it contains the stuff from my last video on ray optics, which was the most powerful formula in ray optics. Yeah, that thing. So first I have just a proof for that in a more understandable language, right? So yeah, that proof that I wrote over there, it contains some errors as well as it also contains some notation that you couldn't understand, right? And now this is written correctly. So we start up at Snell's law, then I mean use this approximation of tan I upon tan r is equal to the refractive index, and then I convert that to the more algebraic form, right? Because we will have to use coordinate geometry. Yeah, so I'm gonna use directed angles just like the last time. Then this time I actually uh, have written down the properties of directed angles, and then I state the problem. So it's just the same thing as the previous time. The problem is you have an object which is emitting rays, and then those rays are paraxial, they are hitting on some surface and they are refracting, and those refracted rays either appear to come from or are actually coming from another point a dash, right? So you want to find where that a dash is, or some equation relating coordinates of a dash and a. And yeah, so yeah, I mean in this step I directly approximated these uh, tan angles like this, so that 1 plus product of slopes thing, that thing I just I mean approximated as 1 because we just want first degree approximations, right? Okay, so yeah, and that's why I didn't take that into account. And then last time I just took h to be 0 comma h without any justification of why I'm neglecting the x coordinate. In this case I am justifying why I'm doing that, because it's a second degree term and we don't want that. We just want the first degree approximation, so we will ease up ourselves by removing that basically. And then yeah, the usual algebra. And then once again the same condition that for any capital H you should have that refracted ray to be passing through the same point, right? And for that to happen, this approximate equation, it should be something like an identity, which only happens if the coefficients of H um, are equal on both sides and the constant terms are equal on both sides, and from that you can get these two formula. So this first formula I didn't actually understand its significance till then, but then I saw it in my booklet and I thought that okay, we'll also see how much this formula is useful. So this is the magnification due to refraction, right? And then this is the actual formula that I wanted to prove, right? And then from here everything I mean falls out very quickly, because you can easily prove the mirror formula, then the lens formula, and all kinds of different things. But it's not over yet, alright, because I have something really nice to tell you. First of all, the mirror formula. So it's done as usual, I mean not as usual, it's done the same way I did it the last time, by seeing how this formula could be applied over here, right? So all I did is just thought that okay, this works if you know what n2 n1 is in terms of this ratio, tan angle I upon tan angle R. So like, yeah, right. So what would happen if your tan angle I upon tan angle R somehow becomes -1? That's the condition for reflection. In that case, your n2 upon n1 thing, that should be -1. So we already know that n1 is just n, right? So the refractive index of whatever medium it is. So we can set n2 to be -n, right? So it's somewhat like cheating a bit, but then it gave me a wonderful idea, and you will see what I mean when I say wonderful. So then I just set this other refractive index. So I don't know where that ray is going, but it's going to some medium which has refractive index of -1. I know the algebra works out, and that's why I'm doing this, although it right now has no physical meaning. So once I do that, I get the mirror formula, right? And also this thing R upon 2 is equal to F, which otherwise you wouldn't be able to prove right away, but yeah, this just dropped down like, yeah, it's obvious, although it's not obvious all of the time. So if you do this with normal geometry, if you want to prove mirror formula from normal geometry, you won't get this R upon 2 equal to F as an obvious condition. No, you will actually have to first of all prove it, and then you will be able to prove this formula, right? And then of course you have this magnification stuff. So right, so using it for this particular case, our n2 is just -n1, and that's why this becomes -v upon u. So for lenses it's v upon u, for mirrors it's -v upon u, whatever. And then this thing, yeah, the shift due to flat interface, this is very straightforward in fact. So not much brain involved in this. I basically just copied what was written in that note into this note, except with more illustration and, you know, making it easy to understand. Right. Yeah. Oh, and also the magnification for this, I mean, slab system. So in each refraction, the magnification is just 1. So yeah, the y coordinate of our images doesn't actually change. And then you have multiple refractions close to each other. So this formula is really useful. So this can be used for, I don't know, to derive lens maker's formula and all kinds of crazy stuff, right? This is the thing. Now sometimes nk will be equal to n0, and this will become even more beautiful, but in its most general case, it's going to be like this. So yeah, lens formula. I mean, this is actually pretty easy to prove the lens formula from here, because we're already at such a high ground. This is yeah. So we do that, we find the focal length using this formula, and then everything. Yeah, once that happens, you go to multiple lenses in contact. So here I define the power, the optical power of a lens. In the previous note, I didn't actually do that. So in that note, yeah, it was just this formula that I was using, nothing else. I wasn't doing anything else. So now all that is now done. Finally, we go to the main part. Negative refractive index, what does it physically mean? Why do we think about the refractive index being negative when we derive the mirror formula? So yeah, at first I was thinking that it's the refractive index of a hypothetical medium behind the mirror, but then I thought that, wait a second, this index varies as you change the medium of the light before it reflects, right? So it must have something to do with going back to the medium, right? Yeah. And I thought, okay, your refractive index is defined by c upon v. What if, so imagine a normal ray just, I mean, hitting the mirror and going back, right? So while it's incident, your ray is along the positive axis, and when it's going to be reflected, it's going to come back, and now it's along the negative axis. So what I thought was, okay, C upon V is a good definition of a refractive index in this case, because right, I mean, it makes the refractive index negative when when the ray is going back. So that idea stuck with me. But then I thought that, okay, what about the rays which are not along the x-axis, so not collinear with that, or anti-parallel to that, or something like that? What about those rays? So we could just take a component of those rays with the x-axis and then take the sign of that. So that's exactly what I did. I defined the refractive index. Right now I'm defining the refractive index. I know this sounds crazy, that why should we do it like this? Why define refractive index such that it accommodates negative numbers as well, right? When are we going to use this? The thing is, you will be using this um, if you actually have this machinery, right? I mean, all of this machinery. Without that, there's no need to do this. But now that we have this new definition, some things become much more doable. So if you, I mean, have this kind of a system, so a bunch of interfaces, but then you also have mirrors in there. What do you do? Do then? You will have to break your flow so that you can actually analyze how the reflection through mirror takes place, and then you will have to continue after that, right? So what we could do is just not break the flow and think of the reflection as refraction. I know that's weird, right? So the thing is, your light ray isn't going to some hypothetical medium when when it reflects. No, it's going back to the same medium it came from, but just in negative direction, and that's why you just make the refractive index negative, and yeah, it all works out perfectly, and then it keeps on going backwards, so you can keep on adding more terms to your right hand side equation, right? Yeah, so this right hand side term, you can keep on adding more things into it, and finally you will get your equation. So the final refractive index, which might be negative if you are actually going back, but then there might be like two mirrors and now you are going to the front somehow. Anyway, the thing is, this is going to be the thing, that the final refractive index, it could be positive or negative upon the x coordinate of the image minus the initial refractive index, which is going to be positive most of the time. I mean, what am I saying? Most of the time it will always be positive, because you will always be taking x-axis along the initial incident ray, right? Yeah. So minus n naught upon x naught, and that's equal to this sum, which might contain negative refractive indices as well. Yeah, so it works out perfectly. And I mean, you had this problematic thing about lens formula, that it only applies when your light rays are along the positive x-axis, right? So even though it could apply if your u is positive, right, it applies in that case. But when in that case does it apply? It applies when your object is virtual, that is, your light rays are still along the x-axis, but they are appearing to go to some point which is having its x coordinate positive. So that's why the lens formula doesn't work the normal way when you have to go from the right side to the left side. But then this formula, it does work, right? Because you will be analyzing these surfaces themselves, not the focal length, right? So the focal length will change when you go from right to left. Before it was positive, now it's going to be negative, because you are going for the different focus, the other focus, right? There are like two foci, and that's why that changes. And in this case, I mean, it clearly shows it changes, but you don't have to worry about it. You don't have to worry about that sign convention at all. So this is perfect, right? What more could you ask for? So yeah, this is amazing, negative refractiveness. And then right away we will prove something for it. So this formula, I just came across it. A friend of mine told this. Where did it go? Sorry. Oh yeah, this formula. So this is basically a lens which has one of its sides silvered, and for this kind of device, you have this equation 1 upon v plus 1 upon u is equal to 1 upon fm, where fm is the focal length of the mirror, minus 2 upon fl, where fl is the focal length of the lens, right? So this is done, I mean, yeah, this is like the usual way of doing it, right? This whole derivation of writing down these three equations for the lens and then the mirror and then the lens once again, but going from right to left. So you write down these three equations and then deal with them and you get this equation, right? So that's the usual way of doing this. You also have another way of doing it, which is of course using our formula, right? So first you just go into this red medium, then you reflect, so you go back to the red medium but now with a negative refractive index because it's going backwards, and then you go to this other white medium, but now this will have a negative refractive index because it's going, I mean the light rays are going backwards. So yeah, you write down these three equations and then you add all of them up. So these are always going to be added up, right? So the thing is, you actually won't have to write down these three equations. You just have to write down the last refractive index is going to be negative and naught, that upon whatever the image x coordinate is, so negative n naught upon v, and then minus the initial refractive index is just n naught, and that upon the initial x coordinate is just u, right? So oh, here I have used x3 and x naught. Anyway, you write that down and then you do this these right hand side terms. So it's like n2 minus n1 upon r, but for each of these interfaces. So first interface you just have n1 minus n naught upon r1. Next you have this mirror which has r2, I mean I'm assuming it has r2 signed radius. In this case it's going to be like negative, yeah. So for this guy you will just have minus n1 upon r2. Then the next term will be so you are going from right to left and then you're going from n1 to n naught, so it's going to be like negative n naught, right? Negative of the refractive index, and then minus once again negative n naught, okay sorry, minus n naught, and all of that upon r2, right? So that's what I did over here. So just add these three terms and then not worry about the cancellation happening on the left hand side. I wrote it down explicitly because just to make sure, right? But in the end all you're going to do is just write down this thing nk upon xk minus n naught upon x naught, right, on the left hand side, and it will work smoothly. And once we do that, you can write it down like that. And yeah, after some rearranging, which isn't that hard actually, yeah, you might think it's like a lot of work. You could have just analyzed this as a focal length of the mirror and a focal length of the lens and do it, right? Yes, you could have done that, but sometimes you won't be given the focal lengths. Instead you will be given the refractive indexes and the radius of curvature. So in that case applying this is easier, right? So now you have two ways of doing it, yeah, for different kind of initial things that you are given. Okay, then you do this thing and you just get this equation, which if you look at it, it's identical to that equation we got. So if you apply the lens maker's formula and the fact that focal length of a mirror is just radius of curvature upon 2, you get the thing, right? So that's what I did here, right? So this is good and all, and finally we are going to this thing, continuously changing index. So how did I come to this? Why did I even think of it? The thing is, our formula n2 upon v minus n1 upon u is equal to n2 minus n1 upon r. It looks much like a difference on the left hand side and a difference on the right hand side. So I thought that maybe if I could make the differences small, then I could write down a differential equation, right? So that's what I did. Although this was different than what I expected it to be. So it didn't just pop out of nowhere. No, you actually had to do some stuff for it. So the way to do it is that you must have something varying with delta x, right? So when you change delta x, that's when the thing should vary. Not if you just go from the left of some interface to right of some interface. Right, that should not be the thing. Instead, the thing we are looking for is something that changes with delta x only, right? So not like very discreetly. No, you want it to change. How do I say it? Continuously, right? So the way I did it is, instead of talking about the images just like we do normally, I only talk about images at points that are left to the interfaces, right? So you have some image coordinates when you are the viewer exactly to the left of this interface, and then you are going to this interface and you sit right left to it, and then you take the coordinates and you take their difference and stuff, and yeah, you will use that to write out the differential equation. So just a quick scroll down and you see what happens out. Yeah, you see what's happening. You finally do get a differential equation, right? And then I have this prism stuff, which is pretty basic. So yeah, I'm done. I've done all of the good things that I could do in this. Now it's time to do the more, usual stuff. So like prisms and telescopes, microscopes, whatnot. Yeah, so I will do that tomorrow, right? Because I have a headache now. Fine. So I'll see you guys in the next video. Bye.